can say the structure of the solids,
solids,
and then the free electron gas in metals. And at the end,
metals.
we summarize a few topics, not all the topics. It's, as I have said earlier, that this is a very lengthy one.
Yes,
But anyhow, we have divided into two or three more lessons accordingly. Now let's see. Solid state physics.
solid state physics. What is solid state physics? Explains the property of solid materials, explains the properties of collection of atomic nuclei and electrons interacting with electrostatic forces, formulates fundamental laws that govern the behavior of solids.
Yes, that governs the behavior of solids. So all these are the basic focusing point, and we will keep all these things according to these three major points.
Yes.
Now let's see the
What
next
is
one.
solid state? Single crystals are long-range order and 3D translational periodicity.
Periodicity.
Polycrystalline
Next.
Polycrystalline crystals are single crystals assembly. Quasi-crystals are long-range order, no 3D translational periodicity. Amorphous materials are disordered or random atomic structure.
So what we can say, all these things are all about the texture. That whenever we
Yes,
are looking at a solid, so we feel something that it may be a single crystal, like just like a diamond. So that is made of the single crystal. So long range order and 3D transitional periodicity and graphite, that is the once again the type of what we can say, the diamond also. So the
yes,
single crystal is always there. So whatsoever the size of the piece is there, so the texture, the first texture of that composition is just only a single crystal, and you can just form uh, this single crystal into according to your need and according to your cutting. Next one is the polycrystalline crystals. So a lot of crystals are mixed together. Single crystalline assembly diamond. So when you are cutting a diamond, graphite it's what we can say the ore form, and pure not a purified form. So diamond is coming from the graphite, and then when you are cutting it, the diamond is the collection of so many crystals. So this structure has been seen over here. So according to the size and the cutting, so this will be categorized in this polycrystalline crystals. The next is quasi crystallines, larger range order, no 3D transitional periodicity. So it's a multiple of the crystals, and what we can say that these have the different type of the structure, not like the similar, not of the similar type. So each and every part is composed by a different type of the structures. Next is the amorphous materials, disordered or random atomic structure. So what we can say, there is no crystalline, there is no pattern. These are of all the random size, and they are all mixed. So you cannot determine any pattern or any design out of it. And maximum of the materials, especially the metals and the other things, are also composed of this fourth form of the solid as per the texture. So what this slide is focusing on, the texture of the solid material. So when we are just
yes,
touching it, when we are looking to that material, if we are just looking to its composition, so definitely all the material is made of atoms, electrons, and what we can say molecules and so many things. But their arrangement is in such a way that further we can categorize to these basic what we can say texture of the solids. Am I audible to you?
yes, you're audible. I
Yes.
can hear you.
Okay. Okay. Well, let's see. The next one is
Crystalline solids. Crystalline materials are solids with an atomic structure based on a regular repeated pattern. The majority of all solids are crystalline. More progress has been made in understanding the behavior of crystalline solids than of non-crystalline materials since the calculations are easier in crystalline materials. Understanding the electrical properties of solids is right at the heart of modern society and technology.
Yes. So this is the first type as per the texture and the composition of that solid, that the crystalline materials are solids with an atomic structure based on a regular repeated pattern. So as we have seen in the previous one, that those patterns are regular and they are repeating the same pattern. So whatsoever the structure is there, but their pattern is just a unique one. How much the size of that material is there, that is just the pattern is a unique. So that is a single pattern everywhere in every size throughout all those material, the solid, whatsoever the size is, but their atomic structure is a regular repeated pattern. So that's why this is a crystalline material. uh, the second property is that the majority of all solids are crystalline. So whatsoever the solids we are using in our daily life, so their uh, texture and the composition of that is a single pattern, regular. That is a regular single pattern, repeating all the way whatsoever the size of the crystal is. The next is the more progress has been made in understanding the behavior of crystalline solids than that of non-crystalline materials, since the calculation are easier in crystalline material. So the mathematically, whatsoever you are calculating the size of that crystal, the thickness, the density, and there are so many features. So that calculation can be what we can say the easier as compared to the other type of the solids, because every time everywhere you are finding the same pattern, and that pattern is going through all the material of that solid. So it's a very easy just to make the measurement or just to make anything out of that. So this pattern will not change. So that's why it's a very progressive in our society, in our daily life use, whatsoever the designing is there, where we are using it. So these have the unique pattern. That's why it's a more progressive in our society, in our daily life in science. The last one is just emphasizing the previous point, that is the understanding the electrical properties of solids is right at the heart of modern society and technology. So that's why the majority of the solids, whatsoever they are, either the minerals or the metals or non-metals, organic solids, non-organic solids, or whatsoever the type is there, so they are being utilized due to this single property, this single structure, this single composition. Because whatsoever you want to use it in any way, so you can calculate its calculation, it's a single base, and you can talk about its crystal, the unique pattern of that. So that's why our society and modern technology and all the gadgets are being made from these type of the solids. Next is,
Crystalline solid.
yes, actually, this
This
picture
is the
is
structure.
a structure, and the picture is stating all about that thing which we were previously talking about. That you can
Yes.
see here
Arrangement is pattern and
imaginary
there's more.
composition of all those particles. So very unique, very beautiful, and everywhere the structure is same. So these balls are connected in a unique way. Similarly, here you can see another metal, that may be a metal or any solid. So this composition and pattern is a unique one. There is no what we can say diversity. It's a unique one, and one more is over here in the black. And similarly, if you can just take the organic compound, so you will get this crystal style, that is once again a unique. And here you can make the whatsoever the instrument, that may be a big boiler that is being used in the atomic reactors. So they are just using that one, that everywhere they must have the same structure, the same texture, the same property, the same strength, the density and other feature. So that's why they are using that. So whatsoever the things are going on over there, so each and every part is equally compatible to that pressure or that radioactivity or whatsoever they are utilizing in the atomic reactors. So that's why this picture is just telling the pictorial view of that, that if you have a thing that has a unique property, so that can be utilized in everywhere mean because there will not be any difference in any further construction. So let's see if the next one is.
Electrical resistivity of three solid carbon states. How can this be? After all, they contain a system of atoms and especially electrons of similar density. And the plot thickens. Graphite is a metal, diamond is an insulator, and Buckminster fullerene is a superconductor. They are all just carbon.
Yes,
But then again,
that's why what I was mixing over there, that diamond is a crystalline metal, sorry, solid. So the reason is that they are basically the basic graphite.
ये मजे
That's why it's a metal, or diamond is a insulator. So whatsoever the metal, the insulator are a superconductor. So whatsoever you are using, their construction is the same. How can this be? After all, they each contain a system of atoms. That what we can say, the system of atoms, that the atoms are arranged in a particular pattern, and especially electrons of the similar density. So electrons, they are all the moving, but they have the same density everywhere throughout the metal, throughout the solid. And the plot thickness, graphite is a metal. So example, a diamond is an insulator, and Buckminster Florence is a superconductor. They are all just carbon. So these are the different format or forms of the carbons. So these carbons are always have a very unique crystalline structure, but that can be refined further just to make a diversity about this. So as in the first crystalline
outlines.
section and interatomic forces, we will talk in the later stage of this. So this is the chapter. Part
Crys-
one is crystal
Crystal
structure.
structures.
Yes, just read it.
Elementary crystallography. Solid materials: crystalline, polycrystalline, amorphous. Crystallography: crystal lattice, crystal structure, types of lattice, unit cell, typical crystal structures, 3D to 14, Bravais lattice, and the 7 crystal system.
So this is all about that, that when we are talking about the crystal structure, so we will have to keep all these things in mind, and we will have to study about that, that this is a once again we can say a science, that is crystallography, which deals with the structure of the solid, of the crystals which are formed in the solid. So it's another branch of knowledge, that is crystallography. So solid materials and crystallography, crystal lattice, crystal structure, types of the lattice, and unit cells, and so many things. So these are all the aspects through which this solid, that is the crystal structures, have been studied. So this is a major division.
Matter, yes.
Matter. So
Matter,
gases,
gases, liquid and liquid crystals, and solids.
solid. So basically, right from the beginning, we used to divide each and every matter into three states, and this division is due to their composition of the atomic structure. So gases, as we can see, a lot of distance between the molecules, and the solid is just composed. So next is classification of solid further.
Classification of solid. Solid materials: crystalline, polycrystalline, and amorphous. And then crystalline divides into single crystal.
Yes, single crystal. So as we have seen these type of the solid, and polycrystalline and amorphous non-crystalline, just like a rock or any type, that has a different composition
That
everywhere,
does
different pattern.
not have a different shape.
See the next one.
Yes. Single crystals. Single crystals have a periodic atomic structure across its whole volume. Along range length scales, each atom is related to every other equivalent atom in the structure by translational or rotational symmetry.
The single
So they are,
pyrite crystal amorphous solid. So two type of the
yes,
basic is that their geometry, their symmetry, their composition, their arrangement of the items
pattern
and the
is very,
molecules are single pattern. Everywhere
yes,
there is uniqueness. That's why this single crystal that all whatsoever the length is there, the scale is there. Each atom is what we can say the equivalent distance, equal arrangement, equal structure, equal shape. So that's why the other this is taking the translationary or rotational symmetry or whatsoever the symmetry is taking place. So they have only one unique pattern of the arrangement that is called the crystal, single crystal. Yes.
polycrystalline solids. Polycrystalline materials are made up of an aggregate of many small single crystals, also called crystallines or grains. Polycrystalline materials have a high degree of order over many atomic or molecular dimensions. Grains domains are separated by grain boundaries. The atomic order can vary from one domain to the next. The grains are usually 100 nanometers to 100 microns in diameter. Polycrystals with grains less than 10 nanometers in diameter are nanocrystalline.
So this is all about that. So I think you have understood all the things. So what is the gist of
Yes.
this slide? Basically, they are the
Uh,
multiple of
it's the
those
subdivision of
subdivision. Actually,
multiple of polycrystalline makes
yes,
crystals.
yes. These are the multiple of what we can say the crystalline, the what we can say the single crystalline metals or materials are coming together and making it a polycrystalline solids. And next is
Yes.
these grain are what we can say domains are separated
Yes.
by grain boundaries.
Grain
That
boundaries.
what we can see in the third structure. So here it has a specific pattern,
They have
but
smaller
immediately after
boundaries within the main.
small
They have
patches,
boundaries, like
just
small
like a football,
boundary patches within the total area.
total area, total metal, that everywhere you will find a unique pattern, and then after that you will get another pattern of different shape, and then you can get the other one that may be separated. So what we can say, it's a textile designing, that on a piece of cloth there are so many shapes are mixing together. Each and every shape has a different color, the different size, a different composition, different geometry, and all that is a different symmetry with all the others surrounding it. So that's why it is called the polycrystalline solids. So here you can see the arrangement of the molecules and the atoms. So some has this one, and
Hmm.
all of the sudden it is getting this shape, and after that
Huh.
you can get another style or pattern, and after that another style of the atom, and the patterns are just changing altogether. None is similar out of this region. Each and every one has a unique pattern. So from here, this is a practical example. The real sample is cut over here, and in everywhere throughout this, each and every portion has a different style, which is never matching with any other. So this can be just taken over here as a grain example, that what we can say, that each and everything, if we are zooming in, so your zoom shape will show all these things, all these pattern. None of the pattern is same. Each and every has a
Yes.
unique one. This is different from
Different
this,
pattern.
and this one is different from all others, and this is also different from all other. Not a single is matching with the other. So that's why each and every pattern is a unique. So that's why it's a polycrystalline solids. This is the summation, or what we can say these collection of the different type of the pattern, different type of the crystal. So it's make is polycrystalline solids. The third one is
Amorphous solids.
yes,
Amorphous non-crystalline solids are made up of randomly oriented atoms, ions, or molecules that do not form defined patterns or lattice structures. Amorphous materials have order only within a few atomic or molecular dimensions. They do not have any long-range order, but they have varying degrees of short-range order. Examples to amorphous materials include amorphous silicon, plastics, and glass. Amorphous silicon can be used in solar cells and in thin film transmitters.
yes. Now you can
Transistors.
explain just in few words how can you sum
So
this?
they are not. So the other crystallines, they have actually a proper pattern. They are just randomly
Yes,
combined together to form a non-symmetrical shape,
yes, good.
and they don't have a proper pattern, which means they cannot be calculated. Like you cannot calculate the density and
Yes,
everything because they're not in a structure, and it's very hard to do that mathematically. And
yes.
then there's
Underlying
some
statement is that
subdivisions of
that nothing is of any pattern. They are at random.
yes,
Just you can put
exactly the
them.
opposite of crystal solid
Yes, yes.
crystalline
Crystalline.
solids.
It's
They
always
are
at random.
symmetrical. These are non-symmetrical.
Yeah, this is a reason that all those atoms and molecules and the proton, the electron, and whatsoever the particles are there. So all the time they are totally random. We cannot visualize anywhere. We cannot make a patch. We cannot just say that this pattern in a very little area is just like the same. So you cannot get even a single patch out of all this. So these are that's why for non-crystalline solids, because there cannot be any crystal or cannot be any pattern. So all the time everywhere they have the different, all the time different everywhere. Not a single collection or not a single pattern is over there anywhere. So that's why these are called the amorphous
Amorphous solids,
solids.
non-crystalline solids.
Yes,
Crystallography. Crystallography is a branch of science that deals with the geometric description of crystals and their internal atomic arrangement. It is important this symmetry of a crystal because it has profound influence on its properties. Structures should be classified into different types according to the symmetries they possess. Energy bands can be calculated when the structure has been determined.
now you can summarize in few words that what is this crystallography.
This is just the branch of science. This is a study of all different kinds of crystals, and this it's important to study the types of crystals and their symmetry so we can have a better understanding on their properties, and
Yes,
that's pretty much, and different types.
structure.
So every different type of crystal has different
Their
structure, and that
structure.
has a unique
There's
properties, and different these properties different types of properties
yes. So that's why
based on the structure.
this is a science, because whenever the material is there and we are just going to make something, so we will have to keep all these points in mind before utilizing it. So we will be in a better position just to make the things according to the nature of that solid. So it's a complete science. Next
Yes.
one is crystal lattice.
Crystal lattice. What is a crystal lattice? In crystallography, only the geometrical properties of the crystal are of interest. Therefore, one replaces each atom by a geometrical point located at the equilibrium position of that atom. It's like a chain. One connects to the other, and the other, and
Yes,
the other, and they all are connected together, and that's why they have a proper pattern,
yes, of course.
uh,
You
organized.
can see the platinum surface, crystal lattice, and
Yes,
surface of the
and the
platinum. So platinum is very costly, even costly than the
metal.
gold. So its structure is of a unique type. So the study of that helps that how the things can be made from this, how this method can be used. So before its utilization, they will have to study its crystal lattice properties, the structure. Next is
Crystal
next.
lattice, an infinite array of points in space. Each point has identical surroundings to all others. Arrays are arranged in a periodic manner.
Yes. So it's a what we can say a geometry and very calculative
Yes.
and symmetric geometry everywhere. So whenever you are just getting the 2 points, 3 points, or 4 points, or other points, so you can say that these points are placed at a specific angle and they have the specific gradients. They have the specific what we can say the altitudes. They have the specific inclination, and they are placed at a specific distance. So whatsoever anywhere you are just getting to make the calculation or just to study the different type of the arrangement, so you will find a unique geometry that is a very symmetrical geometry, and you can make the calculation absolutely perfect for each and every part of that. So that's why it's a very important when they are using it. Next is
Crystal structure. Crystal structures can be obtained by attaching atoms, groups of atoms or molecules which are called bases, motif to the lattice sides of the lattice point. The equal lattice, crystal
crystal
lattice to its
structure
bases.
is equal to crystal lattice plus
All
base.
the crystal lattices are added together to
Added
severe
together, but
version of
in a
crystal lattice.
specific pattern. Added together, it's
Yes,
absolutely right. They are just coming together. But one thing is that is the unique thing that they have been placed according to the scheme, according to the calculation, according to a specific pattern. That if you are just looking all these balls, so these are placed at a specific angle, and each color ball is placed in the same order. If you are putting it
yes,
the making a combination of red and blue, so you will have to put the red below, and you will have to tilt them accordingly according to the pattern. So this will give you that the crystal structure, crystal lattice or plus basis, that how these atoms or molecules are arranged in a very specific way, that everywhere you will find the same geometry, everywhere you will find the same pattern, everywhere you will find the same order of the what we can say the molecules. Everywhere you will find the same calculation, the same inclination, same angle, same gradient, same size, and same pattern. So this is what we can say the crystal structure. Next is
a two-dimensional Gravis lattice with different choices for the bases. These are the
Davis
different.
lattice, basis, and crystal.
Yes,
So
it's
what we can say that here, just like if you are just looking at the bottom, the last one, so it's we can
yes,
say the army of the soldiers. So as we have the
yes,
collection of the soldiers, so you will have to give them a different shape. So we are used to see all
yes,
this in the parade. So the at the initial stage, the parade, the flights, and the squadron and wings are formed in a different shape. When it is just moving, it will get a different type of the shape, different type of the columns. So you might have seen the 23rd March parade, which has been
yes.
telecast
Parade.
on the television. So initially they are formed up in different shapes. When they are moving, so they are getting a different shape, and when they are making a round turn off, they are making a different shape, and when they are passing through that noise, so they are getting the different one, and when they are crossing that boundary, they are just coming together, and a lot of things can be done over here. And the second example is the movement of the dance. So if somebody is dancing over there, so the same hands and the body and the head and the leg and the foot and the whatsoever, each and every part. So for the different movements, you will have to make a specific combination of that. The hands combination, the foot,
Yes,
what we can say matching the footwork, head movements and the body movements. So here, that's why we can say that the two-dimensional lattice is a different choices. That now, according to the requirement, you will make this choice or this choice or this type of the pattern. So as we see now in the mosque and in the social gathering, so when we will have to keep the distance, so the different people are maintaining in a different dimensional distances. So some are parallel, some are vertical, some are zigzag. So a lot of patterns have been observed nowadays because there's no closeness or touchness. That's why the different type of the patterns are being observed. Let's see. This one is
B lattice types.
yes.
B1 symmetries, translations, rotation 1, 2, 3, 4, 5. And 6, there is no 5 or 7. Mirror reflection, reflection about a plane through a lattice point, and inversion operation.
So this is all about that
E-
this can be in this shape or this shape. So all the internal structures have been tilted about the different angle. And here we can say that this is same and this is just going to have a gradient of this. That diagonally it is placed, now it is a horizontally placed. And similar, this is a four-fold axis of cube and three-fold and six two-fold axis of the. So different type of the axes are over there. Axis mean when the two lines are coming across mutually perpendicular to each other, intersecting at that point. So similarly, the planes of symmetry parallel in a cube. So their diagonally is tilted over here and it is placed over here. So different type of the crystal structure can be found by using the lattice type. Next is 5 Travis lattice in 2D.
5 Gravis lattice in 2D. General, rectangular, square, hexagonal, and centered rectangular.
So we
5
have
different
just only
types.
the one rectangle. So it can be
Yes.
placed in this way, or this can be made a part of any cubic,
Tilted or
any
hexagon.
cubic shape.
Yes.
So this may be the bottom of a side pose of a cube. So you can place one more over here, one over here, and one is behind, and one is behind across this one. So the same is placed in a different style, different way. So here you can say just like a laptop, this is a lid and this is whatsoever the keypad area. And this can be make a cube and this can be just adjusted. These lengths, the parallel lengths can be adjusted to get the square. And here you can stretch two lines to get the rectangular shape. So whatsoever is the two dimensional, so you can have a different type of the shape, and when they are getting together, so they definitely they will make a crystal if you are just making more and more. Next is unit cell in 2D.
Unit cell in 2D. The smallest component of a crystal group of atoms, ions, or molecules, which when stacked together with pure transitional repetition reproduces the whole crystal.
Whole crystal, 2D crystal. Now let's see, it's a unit cell, and when they are putting together and making a some pattern, so definitely they are changing position and their pattern. And if you are just going on to put them or fill all these, so definitely there must be a crystalline structure. So all these unit cell, when they are coming together and they are put together in a different arrangement, so definitely they will create the different effects with a different arrangement. And when you closely observe that solid, so that solid will get a different shape and different crystalline structure. So this is all about that. The basic is a unit cell, which is being placed over here and there at a different angle and different positions and different quantities. So these all this we can get a 2D crystalline structure. Now
Unit
3D.
cell in 3D.
How can you explain this? Let's see. It's your perception. How can you see these things?
2D, when 2D are when the 2D structures are formed into a proper crystal, You start forming the
Yes.
larger crystals
Now
based
this
on
is
those
3D.
2Ds.
Now this is 3D.
Yes. No,
So
no, no. You're going to take the 2D crystals and form a 3D structure, and then you're going to form a larger 3D structure.
yeah, yes, we can say all these are the cubical structure, and these are placed in a way that from any angle you can see just the 3D shapes that can be arranged at the same. No, let's see. This is the same one. You have just upside down. You have just tilted toward the left. So you have this one. Just putting it, rotating it to the right. Just putting it right, you will get this up. And if you are just changing the shape, I mean to say, this is just anti-clock movement. So to 90 degree, if we are moving this, so these green parts will become over here. And similarly, these are attached in different way. And if you are just tilting or getting this, so you can also get this shape. So this is the, what we can say, the arrangement of those blocks, those unit cells in 3-dimensional. Next
Three
is,
common units in 3D cells: simple cubic, body-centered cubic, and face-centered cubic.
so once again we can say that if you are using these balls as an atom of that solid, so you can have this arrangement. You can put one more in the center, and if you have some more, so you can just get over here and there. So when you will connect all these one with each other, so outer shape will remain the same, but here you will get the different type of the geometry, and all these symmetrical shapes will give you a different look. That's why when the diamond is cut into different shapes, so it gives a different type of the rays. Similarly, you can have the different type of the prism in your physics lab. So each and every prism has a different property, has a different of the what we can say, the reflection and dispersion whatsoever the light feature are there. So that all depending upon the cuts and the shape and the angles and the structure of those prism. So every prism is used for its own purpose. So here we can say that these four are coming together. So what you can say, that these are all the separated, they are coming together. And one more, when you are putting this in the center, so they must get slightly separated from each other, because now their weight is placed on this ball. And if you have many more, so definitely they will get their own space, and they will be further away from each other. So in this way, what we can say, the simple cube and body centered cube, there is a also a ball in the center, and it's a face centered cube. When you have a lot of the balls, so some colors, some arrangements are slightly away from each other, and some are just coming together. So all reds are closely packed, and whites are slightly away from each other, but they are also closely touched or placed with the red balls. Next is unit cell.
Unit cell. The unit cell, and consequently the entire lattice, is uniquely determined by the six lattice constants A, B, C, alpha, beta, and
Yeah.
gamma.
So
Only one-eighth of each lattice point
yes,
in a unit
continue.
cell can actually be assigned to that cell.
So now
Each,
let's see.
each, okay.
Each unit cell in the figure can be
The figure can be
associated with
associated
8
with
into 1 over
8
8,
into 1/8,
that is
which
equal to
equals
1
to
lattice
one
point.
lattice point.
So what you can say here, it's a very simple geometry. You have the 3-dimensional, the 3 axes, the x-axis, y-axis, and the z-axis over here.
Yes.
And each and every axis has been turned about the 3 angles, alpha, beta, and gamma. So it's all about the alpha, beta, and gamma. If you are making beta greater than this, so this will become over here, this will be tilted to this way. If you are increasing beta, so this will be tilted to over this way. And similarly, if you are getting the gamma closer to this one, so this once again this will tilt in this way. So the same solid, the same cubical shape, but all these are the lines. So these lines are actually, these are six in the way that you have a positive part as well as a negative one. So you have the A, and behind this there is a negative one, and C the Z axis, and you have also the negative Z axis, uh, Y axis, and this is X axis, and this is the Y axis. So anywhere you have the six one, the either you are calculating the positive or negative. So all is it's changing the shape as according to the uh, variation of these mutually perpendicular angles, alpha, beta, and gamma. So when you are decreasing or increasing the values of any one of the angle, so altogether you will have a different type of the cube. That may be a square one, that may be a slightly different one, that may be tilted to the right and the left, and whatsoever the case is. So that's why these 8-dimensional shapes you will get. Next is
Typical crystal structures: 3D to 14 Brabtis and six crystal types: cubic crystal system, hexagonal crystal system, triclinic crystal system, monoclinic crystal system, orthorhombic crystal system, tetragonal crystal system, and trigonal rhombohedral crystal system.
so this is all about that which I was talking about, that whenever you are
Yes.
changing the angles, so you are getting these shape. Cubic, if you are just putting them 90° among all these three lines, you will get a cubic, pure cubic crystal. And if you are just making the angles different, so hexagonal and triskellian and monolith and other types, this is all about that the shape of that can be changed when you are changing all those angles. So you will get these type of the crystalline. Look at this. So and here you can see, as I
Yes.
was saying,
Yes.
that when you are putting perpendicular to all these, that means right angle between all those
9
alpha,
and
beta. So that's why I am saying that when you are putting just the variation of the angles and these three lines, which are six actually, positive and negative. So if you are putting right to each other, you will get this cubic, and if you are just adding the next to one, that you are just closing the third one, B plus C, and angles are the same, so you will get this tetragonal. And if you are just adding these two, making the three lines different length, but angle are fixing, so you will get this type. And similarly, if the three sides are equal, so you will get trigonal, hexagonal, and the other shapes are also there. So this all depend upon the angles and what you can say, the sizes of those perpendicular lines, six lines, x-axis, y-axis, and z-axis. So all
yes,
these
yes.
are depending on that, and this is also what we can say, the geometry of the figure. That is a other branch, what we can say, a branch of mathematics, where these solid geometrical shapes being studies. To calculate the area, the volume, the angle, the surface area, the inner area, and lot of things are there. So next is
Sodium chloride structure. Sodium chloride also crystallizes in a cubic lattice but with a different unit cell. Sodium chloride structure consists of equal numbers of sodium and chlorine ions placed at alternate parts of a single cubic lattice. Each ion has six of other kinds of ions at its nearest neighbor.
so what we can say, this sodium chloride is a table salt, and that can be in a different shape, right from the rock shape when you are getting out of the mines. So different pieces, and now the people are making different decoration pieces with this. Have you seen all those which are made by this
Yes,
salt? So
yes,
basically
salt.
this. can be shaped in can be made of different crystals. So you can also collect the sea salt, and that is purely in the crystal form. Then you will get the table salt just in the powder shape. So here,
This is the detailed structure
yes.
of a
So
cube.
it's a one way or the other. So when these atoms and the molecules are coming together of the different types, so these pink or purple, we can say these are what we would say bigger size, and this is the chlorine of the smaller size. So coming together, so they can get this shape that all around alternatively chlorine, sodium, and this. And if you are just getting more and more, so they will get this arrangement. If you are adding the equal number of sodium and chlorine, so you will get this one. And if you have many more, adding
Then you
just
can,
these quantities, so you will get this. And when you just getting the zoomed figure, that when you are maximizing, you will get the single part, just like a sugar. So you must have seen the refined salt, which is of the bigger size, not in a powder shape. So you can find over there these crystals, these pieces. If salt is just like a Ajinomoto or other type of the salt. So there you can find these shapes. So you can say these
yes,
are the pure crystalline solids. So I
structures.
structure. So this was a first part of this, and you can also go to your book and you can see that. And I will
Yes,
just make the one or two lesson for this because it's
okay,
just we are talking about the first type only. So this is all about that.
yes,
Allah Hafiz. Thank you.
okay. Also, I have one question
Yes, yes,
reg- regarding the physics. So for chapter one, there's I think one topic I'm not very clear about.
yes.
It's in the this chapter is electrostatics. This is about the electric flux. I don't know if we did that or not, but I don't have the presentation for it.
Electric flux.
Electric flux.
Yes, I have.
Well,
I have a
I'm aware.
presentation.
Like,
But
but
anyhow, you can text
okay,
me. Okay, text all those
okay.
things that this is the main topic and these are the things under these
Yes,
topics. So I will check
because
my
it's very complex
presentation
in the book. There's a
in the
lot of
book. Okay, okay.
chapters.
I will see.
Yes, in
Just
my book. That's
one thing more is just you will
yes.
have to text in a way. There's chapter number this topic
Okay, okay.
this, and under
Yes,
that
I will let
topic
you.
these headings are written over there in the book.
Okay.
So I will
Yes. Okay, I
collect all
will.
those things that this is the main and these are the headings and what is there. So I may get the book or other sources of that. So I will make a comprehensive presentation for that. And I'm sure that inshallah that will be clear to you. Okay, thank you very much.
Okay.
Allah Hafiz.
Thank you. Allah Hafiz.